is starting that material. So it's over acids and bases. And believe it or not, a lot of the topics we've actually talked about, introduced. We've talked about like what happens when ions dissolve. We've talked about strong and weak electrolytes. So we've covered a lot of material. So you should see it's something a little more familiar. We're just applying it to this special group of ionic compounds, acids and bases. So acids, originally described as substances that dissociate, which remember that means to separate. So like sodium chloride dissociates, means it forms ions when you put it in water, and it produces hydrogen ions. So that was like originally like a characteristic of acids, sort of like the most basic. So you remember acids make hydrogen ions. So they make H+. Well, if you remember hydrogen, its elemental number or atomic number is 1. It has 1 proton and 1 electron. So if it's a hydrogen ion, what is it really? It's just what? So if hydrogen is a proton and an electron, a hydrogen ion has lost its electron, so you're really just talking about a proton. A hydrogen ion is really just a proton. So it makes hydrogen ions when added to water. So I listed some other characteristics so that you may help in like kind of relating acids, and some acids you've probably come in contact with. They taste sour. Okay, so what's an example of something that's really sour? Lemons. So that's citric acid. So lemons and limes. What is another thing that's sour?
Isn't it the same thing like you hold your tongue to a battery?
That's a little electrifying, so it's not the same as sour. But a good example, vinegar. Vinegar have a sour taste to it, okay, kind of makes your tongue curl. It's the edges of your tongue that are most responsive to sour flavors, and that's why people say it makes their tongue curl. Same thing. But they add lemon juice to cleaning substances because it's really good at dissolving grease. So that's why you'll have like dishwashing liquid with lemon juice added. The acid, the citric acid of the lemons actually helps in removing, breaking up grease, and helps it to mix better in with soaps. Acids, when you mix them with metals, they will dissolve metals and they make hydrogen gas. So this happens to statues. In fact, the Statue of Liberty just finished getting a complete resurfacing. So the metal of the statue, because of years and years of rain, the acidic rain actually was starting to dissolve the surface of the statue, so much so that some of her features were starting to get a little more like flat, washing away. So yeah, they actually had to go in and actually add metals back to the statue in areas where it had started to wear, because acid rain damages things like statues and also changes the pH. So most farmers, they add lime to their soil because the soil is acidic and lime is basic. And so they add it to try and make the pH a little more neutral. So ones that I want you to learn or recognize, the first 3, these are strong acids. And in fact, you've used all these in labs. If you've been in lab, you've used HCl, hydrochloric acid. You've used H2SO4. That's the one that ate the hole in the cloth, like in the first lab. We used that when we made aspirin. Sulfuric acid. Nitric acid is the one that like caused the egg white to get kind of all hard and kind of yellowy looking when in the first lab. That's nitric acid, HNO3. So with these ones, you've got the H out front. That's always a good clue that it's an acid because there's a hydrogen is like part of that, the first element in the list. But the other 2, carbonic acid and acetic acid, these are called weak acids. So remember the electrolytes we talked about last time. Strong electrolytes like sodium chloride, if you put them in water, they separate into sodium ions and chloride ions. Strong acids do the same thing. So hydrochloric acid and sulfuric acid, these are strong acids, strong electrolytes. So when you put a strong electrolyte in water, remember that the arrow goes in one direction. And what do you end up with? So HCl starts off as a liquid. When you put it in water, what do you end up with? Nope. So split it. Just like if this was, what would you say if this was NaCl? If you put NaCl in water, what would you end up with? If this was this in water, what would you have? Na plus AQ and Cl minus also AQ, right? That's its dissociation. Remember we did that with the light bulb? So I put some salt and water and it was like a bright light bulb. Strong electrolytes, 100%. So hydrochloric acid. Hydrochloric acid is a strong acid, also a strong electrolyte. So what is it going to do? It will make what? H plus, there's your hydrogen ions, characteristic of an acid, and Cl minus, also aqueous, 100%. So that means all of the strong acid splits into ions. H2SO4. H2SO4, how many hydrogen ions can it make? 2. So you can end up with 2 H pluses because of the formula. So H2 means I can make 2 H pluses and what's left? SO4, and the charge on that would be -2, also aqueous, 100%. So strong acids are strong electrolytes. That means when you put them in water, they're going to form ions. They can carry an electric current, but the kicker is this. Hydrogen ions are corrosive, and corrosive means what? That it's reactive. So it just means hydrogen ions are reactive. So hydrogen ions don't just sit there and float about. If hydrogen ions come up upon any other material, they're going to react with it. Like the cotton cloth, the sulfuric acid ate a hole in the cloth when you picked it up. Remember, it was completely destroyed because of those hydrogen ions. So this is the same issue that you have with body tissues. Things that are corrosive have to be stored so that they don't come in contact with reactive materials. So when I store hydrochloric acid and sulfuric acid, it gets stored in a glass bottle. It doesn't get stored in a plastic bottle because it would actually corrode the bottle and then it would start seeping out. It would break the plastic down, eat its way through the container. So if you've ever used them in lab, they've always been in a glass container. They're corrosive. Not only corrosive to like a container, but they're also corrosive to any kind of organic material they might come in contact with, like your skin.
So why wouldn't it ever break down the glass?
So the glass is like is really like melted sand, and so it's a really stable form. Sodium hydroxide will actually etch the glass, will actually make the glass look frosted, but the acids don't do that. They're just not. Glass is really something that's pretty inert. It's pretty stable in comparison to other materials. So very reactive with materials. And this is why you take care not to come in contact with large amounts of strong acid for prolonged periods of time, because it can actually break down the epidermal layer deep into the dermis and then go all the way into subcutaneous. You can end up with a burn that looks like a thermal burn, looks like your hand was in a fire, but it was actually exposed to a chemical that wasn't treated correctly. So by corrosive, I mean it can break it down, cause damage, lead to scarring over time. But now remember we talked about weak electrolytes. Weak electrolytes, they don't dissociate 100%. So there, remember, you put the arrow going both directions because it's saying that it doesn't make 100% ions. Only some does. Weak acids are weak electrolytes. So do the same thing though. If we take H2CO3 carbonic acid, What can we make? And in this one, because it's so weak, usually only one hydrogen comes off. So we usually only end up with one. So sulfuric acid is so strong, 2 of those hydrogens will come off. But with a weak electrolyte, we have just 1 hydrogen ion come off. So what's left? With one more, with an H still on it, okay? So in this one, only 1 hydrogen comes off, and in fact, not all of them do, only about 10%. So if you have 10 molecules of carbonic acid, 1 will form ions. The other ones remain associated. And the reason it does this is it's just a more stable molecule. So H2CO3, the interactions of the hydrogens with the carbonate, are more stable than with H2SO4. So that is why they don't just separate off immediately when you put them in water. So carbonic acid, that's what's in your sodas. Okay, that's carbonated soda. It's when they pump carbon dioxide into water to make carbonation. So you drink this all the time. Okay, and it does break down into carbon dioxide and water over time, but it doesn't like cause damage to your mouth. It doesn't cause damage to the esophagus, to the stomach. It's a weak electrolyte, so there's only a little bit of ions that are produced. So less hydrogen ions, less reactive, soda, vinegar, coffee, all examples of some weak acids that you come in contact with pretty regularly. The last one's acetic acid that I've got in my up here, and this one actually is vinegar. And with vinegar, only about 5% of the vinegar molecules actually form ions. 95% remain associated. So it's just a much more stable molecule, complete, rather than forming ions. That's what a weak electrolyte is. Remember we did that one and I put it on the light bulb and it like glowed but dim, didn't glow very much. That's because it doesn't form a lot of ions. So those are ones to learn. So bases. Oh, well. So then these 2 other guys, Bronsted and Lowry, they came along and they were studying acids. And they're like, acids don't just release hydrogen ions when you put them in water. They actually release their hydrogen ions to other things. So instead of saying that they just produce hydrogen ions, they called them hydrogen donors or proton donors. Because remember I said that a hydrogen ion is really a proton? So this is where this term comes about. Acids produce hydrogen ions when you put them in water. They're also considered proton donors. That's a proton. It just looks strange. P-R-O. So an acid is a compound that donates a proton. It was not that different from what the poor little Arrhenius guy said, but they were like, this is much more technical. So they got their own theory. Okay? But those are kind of like the 2 things to look for. Acids are compounds that donate protons, or you can think of them as releasing a hydrogen. They release H or release hydrogen ions. They're giving it off to something else. So bases. So Arrhenius, he said, okay, so when you put an acid in water, it produces hydrogen ions. When you put a base in water, it is going to release a hydroxide ion. The hydroxide ion, remember, is one of those polyatomic ions. These, we've used a bunch of these. Sodium hydroxide, we used this when we made soap. That was that 6 molar sodium hydroxide that you had to use. We used that and put that on that egg white in the very first lab, and it made the egg white kind of get all mushy. Like it started looking like it was getting softer and squishier instead of harder and firmer. And again, that's a strong base. Characteristics of bases, they taste bitter. Okay, like tonic water. If you've ever had tonic water, they add sugar to tonic water, so most of the time, to me, it just tastes sweet. It doesn't actually taste so much bitter. But if you get the diet tonic water, you can taste the bitter just a little bit more. Have you ever bitten rosemary or thyme or sage, like herbs? Herbs are really bitter. You're like, They leave this taste like on the back of your throat, like on the back of your tongue. That is the common place that your receptors are for bitter. Coffee, really strong coffee like the espresso, those are very bitter. So again, back of your mouth or back of your tongue is sort of bases feel slippery on the skin. The reason they do this is the bases, most of them are actually starting to react with these outer layers, and so they don't rinse off as easily. So bleach, if you've ever gotten bleach on your skin, a really weak base is the ocean. So if you've ever been out swimming, your skin feels kind of all slippery when it's wet from ocean water, and that is because it has a pH of about 8. It's slightly basic and has that feel. We used bases in order to react with fats and make soaps. The common ones. The common ones to know, I've got the list. NaOH, sodium hydroxide, KOH, potassium hydroxide, and these are the strong. So just like strong acids, when you put these in water, lots of ions. Okay, they're going to make 100% ions. So if I take sodium hydroxide as a solid, and it's actually like lye, you can buy it in like this white pellet. Take it as a solid, you add water to it, it gets super hot. It's kind of neat. So as it hydrates, it actually releases heat. You can almost make the water boil depending on how much sodium hydroxide you add to it. It's kind of cool. But what happens? If it's a strong electrolyte, what will it make? Na plus, right? Because of the sodium ions, and that would be AQ, and that'll float around, and that's going to leave the OH minus, the hydroxide. It's just like sodium chloride, but this one's sodium hydroxide, 100% if it is a strong base. Now the other three, ammonium hydroxide, magnesium hydroxide, and sodium bicarbonate, these ones are considered weak bases. So just like weak acids, weak bases don't dissociate 100%, just some of them do. So some small percent form ions, the bulk of them remain together. So magnesium hydroxide, when did we use this? Magnesium hydroxide and baking soda or sodium bicarbonate we used in what lab? The antacid lab. Do you remember we used magnesium hydroxide? That was a pain in the neck to get it to dissolve. You had to stir it and bash it about and crush it and everything else. Magnesium hydroxide, these are common antacids. Because when you put them in water, even if they dissolve, they stay together. So they don't make a lot of hydroxide, so it doesn't irritate your mouth. It won't damage your throat. It doesn't bother anything except it gets down into your stomach, and what does it do to the acid? Acids and bases do what to each other? They balance each other or neutralize. And so that's why we use a weak base as an antacid, because it doesn't make very many ions. Those ions are reactive. So this one, NH4OH, so if you take ammonium hydroxide and you put it in water, what will it do? Do you remember what this is? It makes ammonium ions and the hydroxide ions. But
so you would use all
so in this, just some of it would. That's why we have the arrow going both directions. Remember the weak electrolytes have that double arrow. That means when we have this in water, some form ions, but some, well, the majority of it, remain together as a molecule. Hydroxide ions, they're reactive. So they also react with tissues, react with substances. They also are considered corrosive. So they also have the ability to cause damage to tissues. So you try to limit your exposure, but if you come in contact with ammonium hydroxide, because it's a weak base, you're going to have less hydroxide ions compared to the same amount of sodium hydroxide, which is a strong base. So most of the things that we come in contact are weak acids and bases. So they don't have as much of those ions produced, and they're not as damaging in terms of contact. Okay, so those are common acids and common bases, to know their formula as well as their name. So when we're talking about these weak acids and bases, you can see that acids and bases kind of do this complementary reaction. So in this one, ammonia plus water makes an ammonium ion and a hydroxide ion. So in this one, what does ammonia do? So if we look at NH3 and we look at what its most common product is on the opposite side, what happened to that NH3? Yeah, so it gains an H, right? And you can think it gains an H plus or just gains an H. So we said if it gains, whereas this one, looking at water, goes to OH minus, which actually H2O to OH means it loses the hydrogen. So if you gain, that's a base. If you lose, that's an acid. So do you notice how they one gets transferred to the other in a acid-base reaction? So this ammonia is the base, water is the acid. So all that you're doing is just look at the reactant, find the most common form on the product side to determine, did it gain a hydrogen or lose a hydrogen? Did it gain an H plus or lose an H plus in that reaction? And that can allow you to identify what the acid and what the base is. So look at the top one. Hydrogen chloride plus water makes hydronium ions and chloride ions. So what happens to this? Right? So you see how you end up, you go from HCl to just Cl. So that definitely loses the H. That makes it a. Where's water? And so if you gain, that's the base. That happens 100% because I said that hydrochloric acid is a strong acid. So notice the arrow goes one direction, not both. But then the bottom one, ammonia plus water makes the ammonium ion and the hydroxide ion. See how the arrow goes both ways? That tells you that this is a weak acid and base. But still, the acid is the component that is going to lose the hydrogen ion. The base is the component that gains it. So both of these are examples of what happens when you put acids and bases in water and how they then release hydrogen ions or accept hydrogen ions. I already gave you those ones. So he said, though, if I take an acid and a base, that's neutralization. So a strong acid, so an easy strong acid, HCl. An easy strong base, NaOH. If I take a strong acid and I add a strong base to it, do the double displacement for this, what will you make? If you swap pairs, so the H could combine with what? It's always the outer pairs and the inner pairs. So H and OH makes, H and OH is HOH or, water. And then the inside pairs are?
Cl.
So which goes first? So you can take a strong acid like hydrochloric acid. That's like toilet bowl cleaner. So hydrochloric acid is commonly used to clean all the grossness from the toilet. Sodium hydroxide, that's like Drano. So you can take toilet bowl cleaner and Drano and mix them together, and all you'll have is salt water. So they neutralize. Two very reactive molecules become much more stable as just a salt solution. That's the neutralization. So you do this when you have acid indigestion, but you're not going to drink sodium hydroxide. So yes, you have hydrochloric acid in your stomach. And so like for me, it's always when I go to LTAP. Okay? So LTAP is the challenge because I think it's the cilantro and the limes and all the tomatoes and the onions. And then the jalapenos and everything else. And so then, you're like, oh. That, and it's probably the volume too, because you're just like, oh, I'm not going to eat this. Okay, I ate everything. All right, so in this, if you have too much acid in your stomach, excess stomach acid causes all of those negative side effects. So for people that have a weak esophageal sphincter or cardiac sphincter, gastroesophageal sphincter, whatever you want to call it, if they have a weak sphincter, then acids and food get pushed from their stomach up into their esophagus. And the esophagus is not designed for stomach acid. Your stomach makes all kinds of mucus so that it's always kind of like greasing the walls so that the acid doesn't really bother it. It's not the stomach that actually is the issue, unless you have an ulcer. It's not usually the stomach, it's typically your esophagus. So if acid gets pushed into your esophagus, that will cause inflammation. And oftentimes people start describing this like pain right in the middle of their chest. Sometimes they think they're having a heart attack even because the pain can even start getting higher and higher because of that esophageal irritation. So to combat this, they take a weak base. And that's what antacids are. Aluminum hydroxide, magnesium hydroxide, calcium carbonate, sodium bicarbonate, all of them can be used. They're all weak bases, which means that they don't make a lot of hydroxide ions, but there's still a base that will react with acid. And acids and bases make salt and water. So even though they're not strong, that's actually the better way to ingest them so they don't cause any kind of damage to body tissues. They just react as they get down into the stomach. So calcium carbonate, that's the one that they put in what? This was like the way that so many people were getting calcium. In Tums, right? So they like talk about like, oh, it's got calcium in it. I don't eat that anyways. Okay, so you tell me, how soluble were those Tums? Not very soluble. In fact, do you ever eat antacids? Do you know how chalky they taste? So they leave this kind of grittiness to them. So they're weak acids and they're not very soluble in water. So that calcium form is not as absorbed as well as your dairy calcium. And so that's why they really say it's really not an equivalent. You will get some calcium, but you're not going to get as much calcium as you would get from any kind of dairy type of supplement. And there's even some calcium supplements that are different salts that are better dissolved, better to be absorbed for people that try to improve their calcium intake because they don't eat a whole lot of dairy. Other interesting things, if you take sodium bicarb, baking soda, remember when you put it in the acid, what did it do? You put baking soda and acid together. It fizzed. Did you notice that? That's carbon dioxide. So if you take NaHCO3 and HCl and do a displacement, the sodium is going to combine with what? So we still end up with salt. And you still end up with H2O. So there's an H from the hydrochloric acid and an H and an O from the sodium bicarbonate. But what's left over? CO2. One of the O's ends up in water, so the other one, this is the gas. This is why you get the bubbling. And so if you've ever used baking soda as an antacid, you'll burp a lot. So you're like, and that's because you actually produce a lot of gas in the stomach that then you end up burping. Okay? So when we have these weak acids and bases, we say we have that double arrow. So that double arrow means that some of the reactants will form products. And eventually some of the products will go back and form reactants. So that exists at this balance. And the balance is called equilibrium. So equilibrium occurs when the forward reaction equals the reverse. So if you take nitrogen and hydrogen two gases, combine them in a container, you will be able to form ammonia, NH3, and eventually the forward reaction will stop and you'll start to have some reverse reactions with it until eventually forward and reverse are exactly the same. When you get to that, that's equilibrium. So I think of equilibrium as being this. That is the balanced seesaw. Okay? So that is when my reactants and my products are balanced. It doesn't necessarily mean I have 50-50. Because like we said with vinegar, 5% of the vinegar molecules form ions. 95% don't. But that's equilibrium. That equilibrium, it does not necessarily mean you have equal amounts of reactants and products. Equilibrium just means that you reach a point where forward and reverse reactions are the same. So there's no net change. So this does not mean that reactants equal products. You can have 99 product, 1 reactant, and have equilibrium. You can have 99 reactant and 1 product and have equilibrium, or you can have 50-50. You can have any variation of them. It's just where the forward reaction occurs and then the reverse reaction starts to happen. And when they begin to happen at the same rate, you've reached equilibrium. So a way of being able to describe, do I have more reactants or do I have more products, is to look at what's called the equilibrium constant. So the equilibrium constant is just a ratio. It's a ratio of products divided by reactants. So at equilibrium, if I have a lot of products, will my number for K be big or little? So remember I said, okay, well, if you have 100, so I start off with 100, and now I have 99 reactants, and I only have 1 product. But I still reached equilibrium. That's at the balance. What will my K value be if I have like 1 over 99? A decimal? Do everybody agree? It'd be a small number, like a little 0.00 number. So a small number means very little product. Compared to reactant. But what if it was exactly the opposite? So what if I had 9, so maybe I had 10. So if I start off with 100, I have 10 reactants and I have 90 products when I'm done. If I put 90 over 10, what is my K value going to be? Really, really small? It would be 90 over 10, which is 9. So it would actually be a big number. So in this one, my K is greater than 1. It would be like 90 over 10. And that tells me that I have lots of product. More product, less reactant. So that's really the value of K. And in fact, in many reactions, the equilibrium constant is known. And that way you can actually tell if your reaction is done. So if you take reactants, mix them together, and you have this amount of product and you know your equilibrium constant, you can actually figure out if your reaction is finished. So if it's not there yet, then you've still got some more forward reaction to do. But what happens if I change reactants or products to a reaction that is already at equilibrium? So I said, all right, well, A goes back and forth and it makes B. So in this, we can do the one that we just did before. So I said, okay, well, what if I have 90 and I have 10? Started off with 100. And now at equilibrium, I have 90 products and I have 10 reactants. And my forward and my reverse reactions are like done. if I add or remove anything, that's going to change the equilibrium. So right now I'm here. So what if I dump in 50 more A? Now I have 60 A, and I have 90 B. So what do you think is going to happen? It's not at equilibrium anymore. But I want to make my equilibrium so that I'm kind of like, for every 10A, I have 90B. So what would I need to do? But I want my reaction so you can kind of think, so now I have a lot of reactant. I don't have a whole lot of product comparatively. How do I bring that back into equilibrium? I don't want you to figure out the exact number, but what would happen? How would I fix this? How do I bring the seesaw back into the balance? Which way would I have to move the reaction? Forward or reverse? So you can think of like your reactant side's really heavy. So what do I need to make more of? The product side. So you see, if I take some of the reactant and I convert it into product, that I would like bring them back into a balance. So the forward reaction would occur, and I'd probably end up with somewhere around like 15 and 135, because that was my initial ratio in order to bring it back into balance. It's not the same amount, but the ratio is back. The relative amount of A to B back into balance. So rule in this is, if I add or remove, if I add reactant, the reaction shifts away from whatever I add. So that's why I said it would make more product. So we would say that the forward reaction would occur. So what happens if I could pull away or siphon off B? If I siphoned off B, then the product side would be less, and so I'd again have to have a change in the reaction to bring it back into balance. So now I'm at 15A at equilibrium with 135B. And so now I'm just going to take out 35B. So that again is going to take my balance. It's going to make my products now less compared to my ratio with the reactants. And so if it's like this, how do I replace it? What would I have to do to bring the balance back? Which direction would the reaction have to go? Forward or reverse? Forward again. So I would actually take more reactant and convert it to product. So the forward reaction occurs. So this explains, or this you can use as kind of like a general rule. If you have a reaction, and it doesn't matter if I have A plus B and C making D, E, and F. It doesn't matter how many products and reactants I had. If I have a balance, so I have to be at equilibrium, if whatever I add, the reaction always shifts away from whatever I add. Because whenever I add, that side's going to get heavy. So to be able to make it balance, I'm always going to shift the reaction away from what I add. No, go ahead.
Okay, you started off with 100A, right? You got 10A and 90B. You added 50 to A, which made it 60 and 90 to B. So why would you go from the reactant to the product?
So in this ratio, this is the ratio at equilibrium. I have 1 part reactant for every 9 parts product. Okay, so that means that if I add reactant, then if that's the balance ratio, that means that now I have more reactant than I did initially at equilibrium. So I add A, so this side goes down because it's reactant. Can you see that part? So it doesn't have to be 50-50. okay? It can be any amount. So I have a balance of forward and reverse reaction occurring. That's really what equilibrium is. Equilibrium doesn't say that I have to have equal amounts of reactant and product. It just means that the forward and reverse reactions are the same. So in this one, I'm at equilibrium. I have 10A and 90B. So every time 1A goes forward, now 1B goes back. So forward and reverse. So I have like sitting in the beaker, 10 parts A, 90 parts B. So if I add A, that ratio is now imbalanced. So I've added reactant, so it's going to make the ratio of reactant to product out of balance, and the reaction will shift forward to try and restore that ratio where I have 1 part to 9. Okay? So reactions always shift away from anything that's added. It doesn't matter if I'm adding to reactant side or adding to product side. Either one, it'll shift away from it. The reaction will always shift towards anything that is removed. So in the first example here, I'm adding reactant. Do you see that the reaction shifts away from the reactant side? So the reaction goes forward to try and restore the balance. And then the second one, I removed B, and so the reaction shifts forward to try and replace the B that I removed. So both times, the reaction shifts forward, and it's going to do that until you get back to the balance and the forward and reverse reactions become the same again. So let's look at a couple of other ones. So here. So if I have, and this one takes into account that heat energy, and this is an exothermic reaction, which means that heat is a product. Heat is released. So what happens if I add H2? So if I'm at balance and I add H2, first figure out where is H2 in the reaction. Is it a product or a reactant? It's a reactant, so you see that it's here. So if I add a reactant, which way will the reaction shift to restore balance? Because it's going to make it like this. If I add reactant, the reactant side becomes heavy. I have to do the forward reaction in order to bring it into balance. What if I add NH3? What if I add NH3? What is NH3? So what's that going to make my seesaw look like?
Oh, you're adding it. It's obvious.
So it's going to make that side. So it's going to actually make my product side heavier. So what reaction has to occur? The reverse. And it's not going to take place forever. It's just going to take place in reverse until you get it back into balance. So what if I remove N2? Because what is N2? N2 is a reactant. If I remove reactant, the reaction always shifts towards whatever you remove. So that means that it would end up being like this. Again, removing N2 would make my reactant side light, And so the reaction is going to shift in reverse to try and push it forward. What if I take this and I cool it? What if I take away heat? Oh, what is heat? What would it be considered? It's I think you said it. Yeah, it'd be a product. So in this one, if heat's the product, what's my seesaw going to look like? If I remove heat, then it's going to end up creating this. Because I've taken away heat, so the product side is lighter. So which way will my reaction go? Forward. So if I had an endothermic reaction, I would have heat on the opposite side. Like heat would be a reactant in this one. Heat is a product. And so if I had changes in heat, you can use that just as if it's a product or reactant depending on its position. So here's sort of like the summary for them. Okay, what happens if you add or remove reactant and which way the reaction will shift? This only happens once you reach equilibrium. You've got to have equilibrium, equal forward and reverse. If I add reaction, then see that the forward reaction, this would be forward because the reaction shifts to the right, which would be a forward direction. If the reaction shifts to the left, that's the reverse. And then in terms of the temperature ones, if it's an endothermic, where would heat be? It's a reactant. Whereas if it's exo, then it's a product. So that tells you where to put it. And this only works for reactions that have forward and reverse reactions. They're reversible, where they have equilibrium. Some of these reactions are not equilibrium reactions, like bleach. So bleach is sodium hypochlorite. When you put it in water, you smell, what do you smell? What's the bleach? What's the smell you smell? Look at all of the things that are made. It's the chlorine, okay? So you get this chlorine, this is a gas. Oxygen, this is a gas. So this is a one direction thing because these gases evaporate, so they're gone. So unless you can contain all of this, you have to be talking about a reaction where you're going to see this, okay? So equilibrium can exist in reversible reactions. There are some reactions though, like when you burn fuel, those are irreversible. Okay, so you're never going to see the arrows going both directions with those. You have to see that double direction. Here's the example connecting back to what we talked about with gases in the last chapter and how gases diffuse from high concentration to low concentration. So this reaction, the top part, all of this red part at the top, that happens in your lungs. So you take a breath. You bring oxygen into the lungs, so air comes into the lungs. Remember that we said when gases are at high concentration, they will diffuse to low concentration. So oxygen diffuses into the blood. And inside of the blood, there is a protein that we'll talk about in the next chapter called hemoglobin. So hemoglobin sits in the red blood cell. But when oxygen comes in, look what it does. It swaps. So this right here, you can't see it, is actually an H+. So what does the hemoglobin do? Does it act as a proton donor or acceptor? HB. Yeah, it loses its hydrogen. So proton donors are this, you would say, going from here to here. So if you lose a hydrogen, it's a acid or base? It's an acid. So if we lose H+, that's an acid. So that swapping that can occur does generate hydrogen ions. Now, when the hemoglobin gets to your tissues, so these are the capillary beds, like in the skin surrounding your muscles, all along the capillary beds of the brain. When it reaches that, then you have, at the tissues, the cells have very low oxygen and the red blood cells have very high oxygen. And that's enough to actually shift the reaction the other direction. So as oxygen moves out, so like as oxygen moves out of the blood, that triggers more release of oxygen from hemoglobin. And it's really that equilibrium. So that shifting is going to help to push oxygen out of the blood, push it into the cells, and allow the cells to use it for energy. And it's all on that premise, that diffusion premise. Things move from high to low concentration. But it's really an equilibrium balance that allows for that movement. If you're looking at a strong acid versus a weak acid, which one of these is a strong acid? The left one. And so how many ions do you see? How many of them have a charge? All of them, right? So there is 100% ions that are produced. So hydrochloric acid in water, 100% of ions are made. But look at the vinegar. So when you look at the vinegar, most of these CH3, COOH molecules, there's no charge to them. Most of them exist as just the molecule, but there's one here and there's one right here. So just a few ions are made. That's the characteristic weak. That's the weak acid, and that's the one that only about 5% form ions. So the last topic in this before we talk about pH is what happens when weak acids and weak bases combine. So weak acids and weak bases, they'll still neutralize each other, but they will exist as an equilibrium balance. So in this, the acid is always going to give up its hydrogen ions. The base is going to gain them, but it will make a pair as a product that'll be sort of like the mirror image of that acid and base pair. So if I have HA plus B, in this reaction, I don't know what that C is. In this reaction, if this is my acid, it is going to lose the hydrogen ion. If this is my base, it's going to pick it up. So my product will be A and HB. There's the swapping. So the hydrogen just got swapped from one to the other one. But if it's a weak acid and base, it doesn't split up 100%. So instead, I actually end up with an equilibrium so that A can react with HB and reform HA and B. So in the reverse reaction, which one of these is the acid? The HB. So they call this the conjugate acid. Whereas A, which acts as the hydrogen acceptor, see how A goes back and becomes HA on the reactant side? This is the conjugate base. So the thing to remember is the acid always, a weak acid will become a conjugate base. A weak acid donates a proton, but in the reverse reaction, its conjugate base will accept it. So a weak acid will become the conjugate base. And a weak base will become the conjugate acid. It only happens if it's weak, okay? If it's one that doesn't dissociate 100%, one that you're going to end up with an equilibrium of these. So you can see this in this bottom one. So if you look at CH3NH2, go over to the opposite side to compare what happens to CH3NH2. It becomes CH3NH3+. So it gained the hydrogen and going in that forward direction. And so going adding or gaining the hydrogen, characteristic of the base. That is why it's the base. But if I was looking at the reverse reaction, CH3NH3 plus, going in the reverse is going to lose it. So that is why they call it the conjugate acid. In this one, water loses its H plus, loses its proton to become the hydroxide ion. So the acid loses its hydrogen, characteristic of acid. But if I go from OH minus and look in reverse, that acts as a base, which is why they call it the conjugate base. So we can do some of these ones in sort of identifying them. So what you want to do with each one is look at the reactant and find the pair on the product side that looks the most like it. So for HCN, which looks the most like it? So CN minus, right? So then the next question is, okay, well, what happened? Lost the hydrogen. So if it loses a hydrogen, that makes it an acid. So then on this side, my CN minus going the opposite direction is going to gain a hydrogen. So it is a, but on the product side, it's always the conjugate. Okay, and that way you can identify which one is the acid in the forward reaction. The conjugates are the acids and bases for the reverse. So now NO2, most like NO2 minus, gains a hydrogen, and that makes it a base. So that means HNO2 in the reverse reaction is the conjugate acid. These really are not hard. It's just a matter of sort of like identifying what happens to each. Just remember, on the reactant side, you have your acid and base. On your product side, you have the conjugate acid and base. Your weak acid always forms the conjugate base on the opposite side, and the weak base always forms the conjugate acid. So see if you can figure this one. So NH3 becomes, so it, that makes NH4 the, H2SO4 minus, that means it's a acid, right? Acids are always going to lose the hydrogen, bases are always going to gain. So that makes the SO4 2 minus. Okay, and you understand what I mean by conjugate base. If I took and look at this reaction going backwards, if I go this way, I would say that NH4 plus loses a hydrogen, and that's why it's an acid. And then if I look at SO4 2 minus, I'd say that it gains that hydrogen, that makes it a base. So the conjugate is just the way of describing the product side, and you don't use that on the reactant side. So it's just a way, so I can actually define an acid, a base, a conjugate acid, and a conjugate base in a weak acid-base reaction.
So where did the 2 minus come from? That's what started.
Oh, the 2 minus. So see how it was HSO4 minus? So that was the hydrogen sulfide molecule. So it lost another H plus, which is why it ends up with a -2. Remember, because the H's are plus. So I went from HSO4 minus, I lost another plus, so that's SO4 2 minus. Okay? And you really won't have to worry about the balancing of them. It's really just picking them out. And so the key thing, look at the reactant side, find the pair that matches it on the product side, and define, did I gain or lose a hydrogen? So H3PO4 looks the most like.
H2PO4.
So that what happens?
Lost the hydrogen. So what is that acid?
So that means that NH4 plus is the. And the H2PO4 minus? Now this is different than what happens if you're reacting a weak acid and a weak base and a strong acid. So this one, calcium hydroxide and HNO3, if one of them is strong, then that means it's just going to keep on making ions until you have what? Acid and a base makes what is always formed. The outside ones and the inside pairs. Yep, so Ca and NO3 and
HO4.
yeah. So if you're talking about, so HNO3 is nitric acid. Okay, so nitric acid, this is a strong acid. Single arrow. Not the double arrow. That's one way of trying to is identifying strong versus weak. Weak acids will form equilibrium. Weak acids and base reactions, we're going to end up with the arrows going both directions. Whereas if you have a strong acid involved, it is going to react until it's completely gone. It's not going to go back and forth. It's just going to neutralize. And so in this one, and you would actually end up like, so calcium's +2, the nitrate's -1. So you'd end up with 2 of those. That would just balance it. You'd have 2 waters if you're going to balance the equation itself. And 2 nitrates. Just have to add the balancing in. But that you'll see, and I would use a single arrow. Okay, so if you see a single arrow and you see an acid and a base pair, you know it's a strong acid and base. And they're just going to neutralize. Whereas the top one ends up forming a balance of acid and base all present in that solution. So this is a question that's in chapter 9, so it's pages 362, and it says, identify the acid and the base and the conjugate acid and base in the following equilibrium reactions. So look at those ones. So what happens to H3PO4?
It loses a hydrogen.
And then this one? Exactly. So there's this one and this one, and then some of the base, like those are ones to see if you can just react. I won't give you, like I won't make you finish a reaction, but with these ones you should be able to identify the conjugate acid and base pair. We'll do those ones next time. So the last topic is really pH. And so pH is a measure of the amount of acid or base that's present. So what they did is they estimated when water is in solution, water itself, because water can act as a proton donor, water can act as a proton acceptor, that water is actually like its own little acid-base reaction. So in this one, can you see how this water molecule acts as an acid. Do you see how the red water, or the first water molecule can actually lose a hydrogen? The second water molecule can act as a hydrogen acceptor and go from being H2O to H3O plus. And so there was like, well, how much does this do? So when this is at reaction, what is the K? What is the equilibrium ratio? The equilibrium ratio is the amount of acid relative to the amount of base. And they found that it was extremely small, 0.1. That's the K value. Super, super small. It is 1 times 10 to the minus 14th. So that means there is very little, like 0.00001% form ions, 99.9999% stay associated. So water doesn't dissociate very much. In fact, when I put distilled water on the light bulb, did it light up? No. And it does make ions, but it's so few ions, it's really considered a non-electrolyte. Very, very little ions form. Not enough to actually carry a current. So in fact, if you were in distilled water and someone threw like a hairdryer in the distilled water, you would not electrocute because there would not be enough ions. The problem is what's on the surface of your skin? Salty sweatiness. And so when you get in the water, and that dissolves off the skin, and that's why anything added to the water then would carry an electric current. But if you were actually kept like free of any ions being secreted from your body, pure water does not make enough ions to carry an electric current. But they said, well, this is kind of like our smallest amount possible. So we can start looking at other acids and bases and talk about it relative to this scale. So this left us with the pH scale. So they said with the pH scale, water has 1 times 10 to the minus 7th molar hydrogen ions, which is H3O plus. So water has 1 times 10 to the minus 7th molar hydrogen ions and 1 times 10 to the minus 7th molar hydroxide ions. They're about the same. That's why that K value is 1 times 10 to the minus 14th, why it's so small. So you see here that H plus is equal to OH minus. The acid and the base are equal to one another, and that's where they came up with that midline on the pH scale. That 14 became like the lowest amount of acid possible, 0, the highest amount of acid possible. So you can see it in this one. So here, in an acidic solution, you have more hydrogen ions. H plus is greater than OH minus. So you can see that the H3O plus, which is the same as saying a hydrogen ion, more of those compared to the base. So we have more acid molecules, less base molecules. That makes sense because it's an acidic solution. When we're at neutral, the acid and the base are equal. When we start to go into the basic side, the hydroxide content goes up and acid levels comparatively is low. So here now we have more base and we have less acid. So it's really a comparison of the presence of the two of them, what their ratio, how much acid compared to how much base you have. So if you were to talk about actual concentrations, a lot of times your acid or base concentrations would be a whole bunch of zeros. So like if you were talking about like coffee, so coffee, you would say there's 0.00015 molar H3O plus or acid. It's a little acidic, but then you've got all these decimal places. And so the pH scale is a logarithmic scale. So logarithmic means it's all on factors of 10. So every time your pH changes by one number, that's actually 10 times more or 10 times less acid or base present. So the log is a base 10. So if I have 0.1 molar HCl, when I put this into the calculator, I would find the pH, because this is a strong acid, I would find the pH. It would be minus the log of 0.1 molar. So how many decimal places is that? 0.1 molar is, to go to 1, you just have to move it. So you'd just be moving it 10. So a factor of 10 would be equal to 1. So that would be a pH of 1. If I had a 0.01 molar hydrochloric acid condition, do you see that that's 10 times less? So it'd be like 10 times more dilute. So what would the pH be? How many decimal places? 2. The pH would be 2. So it's 10 times less, so the pH would be 2. So the pH in this is really like a measure of, like, by factors of 10, how much different a acid content is in a solution. So some of the common ones, and then we'll quit. We'll pick up and we'll do some pH calculations next time, finish up with buffers and go on to chapter 10 on Wednesday. But when looking at the scale, here's neutral, here's 14, here's 0. So in that scale, some of the common ones, so right at pH 7, pure water. Because remember, we said that water is equal amounts of acid and base, very little, but still equal. The higher the acid content, the lower that, the larger the decimal place will be for hydrogen ion. So this is increasing acid. When I go from a pH of 7 to pH of 6, that's 10 times more acid. The pH of 6, things like milk. You don't think of milk as being acidic, do you? It's pretty, they call it a mild acid because it really doesn't have a lot of acid in it. It's much more closer to being equal acid and base. pH of 5 even, that's the one I was getting up with coffee. So the rainwater, remember I told you that rain is acidic? It's not super acidic, but it is a little more acidic because of the metal oxides in it. Urine, coffee. Again, these are all considered mild acids. Mild because there's not a lot of hydrogen ions, so they're closer to 7, less corrosive, things you come in contact more. pH 4, tomatoes. Some people, a lot of coffee and a lot of tomatoes give them indigestion because it's higher acid content than things like milk. So you have tomatoes, soda, because it's got carbonic acid in it. So it's going, the acid levels increase. When you get much below there, these are the ones that you start to really notice the sourness, vinegar, lemon juice. Remember I told you that vinegar is a weak acid, but it still has a higher hydrogen ion concentration than most of your foods. So you do eat some vinegar. Some people like drink vinegar. Can't do it. Some people do. Claim it's like, you know, the ways to keep yourself alive, I guess. But lemon juice, even though it's a weak acid, it's still really low on the pH scale. Okay, typical vinegars around a pH of 2. The ones around a pH of 1, that's your stomach acid. Now, do you notice that there's a negative 1? So the negative 1 is concentrated hydrochloric acid. We use that in lab. Under normal conditions, nothing naturally found would have a negative pH. But you can make concentrated hydrochloric acid in a lab or in a like a tech company can produce it, but it's not normally found. So normal things, really stomach acid is the most naturally occurring acidic material known. Even battery acid is something that is artificially man-made. So really we kind of just go all the way down to 0. I don't really kind of count those ones because you don't see those in nature. Those are all acidic. Those up close to 7, mild acids. Those down low, these I called strong acids. Strong acids, these are the ones that are more corrosive. The ones that you really do watch for. And you can actually have very dilute hydrochloric acid. It's a strong acid, but if it's very dilute, then it's going to be more like water. Going above 7, that is where hydroxide levels start to get larger than hydrogen ions. So notice in here, the ocean. So I told you it feels pretty slippery. It's like right at a pH of 8. Baking soda. If you brush your teeth with baking soda, it leaves your teeth like feeling really slippery. Same thing, same sort of sensation to it. Soap. These are all things that we come in contact on the regular. When you get much above 10 though, then you start getting into the ammonia, bleach, hair remover, oven cleaner. So hair remover is like the Nair. Have any of you ever used Nair? Have you ever used that? So what Nair is? So Nair is actually like a potassium hydroxide like paste. It's like a lotion. So you put it on your skin and it actually dissolves the hair follicle. So it causes, not the hair follicle, the hair shaft. It causes the hair shaft to actually unwind. So the hair itself is like all of these little skin cells that have been formed into a shaft as it comes up through the follicle. So this stuff is so strong, it actually causes those cells to unwind, fall apart, and then you just like rinse and it's gone. So your hair is like, boom. And then what's your skin like afterwards? Have you ever done that? Huh? It's all burns, yes. And then you're all red and rashy because you have like a mild chemical burn because of exposure to it. But that's how it works. When I was a kid, my mother used to make us clean the oven. We didn't have a self-cleaning oven. And so that was the easy off oven cleaner. I don't know if you've ever used any of that. Oh, good gosh. Like you'd be all red and raw, like, my hands are burning. I'd be like, get in there and scrub in that back corner. Like, no. She's like, you're little, get down there. But that was like a common thing in the summertime, one of those chores. Can't I dust? I'd rather dust. But cleaning the oven, but that's again, because really strong hydroxides, really good at dissolving grease. Remember, because it like literally makes it into soap. So it helps to dissolve all of that and clean all of that. I'm really glad I have a self-cleaning oven now. I never did that to my children. But up here, super strong base. Oven cleaner. Drano would go in here too, because it dissolves all the greasy kind of stuff that collects in the drain. Very strong base, corrosive again. High amounts of hydroxide ions cause damage. Really, much above 10, you really do try to limit your exposure to. So ammonia, bleach, hair remover, Drano, and the such. Whereas the soap, egg whites falls in here. Egg white's kind of slimy. Okay, characteristics of bases that they're slippery. Also okra. Has anybody ever eaten like steamed okra? Are you a fan?
I'd rather have tried.
Fried. Not the fried. Like, have you ever had like the boiled okra?
Oh, yes.
Woo! And you like, you know how it's like slimy? And so you like, so the lady that used to make it, she was like, it slides right in, it slides right out. Voila. You don't have to take a laxative. You're all good to go. But that falls up in there too, because it really has that kind of slippery, slimy kind of flavor, like feel to the texture of it. That's there's not a lot of foods. We don't actually eat a lot of basic foods. Most of the foods that you eat fall into the acidic category. They're either neutral or slightly acidic. But those are a couple of the ones: baking soda, okra, egg whites. Okay, all right, I'm gonna stop there. Oh, that's not it. On Wednesday, we'll go back, we'll do a couple more acid-base, conjugate acid-base examples, and then we're gonna do pH, and we're gonna talk about buffers, and we're gonna be finished with this chapter, and we're actually moving on to chapter 10.